All right, guys. So Unit 5 is kind of an extension of Unit 4. A lot of like increasing, decreasing concavity, and we're going to do some curve sketching here, okay? Okay, so they call this the curve sketching recipe, basically like how we go through here. All right, let's look at each of these steps. Step 1, give the domain. Now, if we're doing a polynomial, the domains are just all real numbers. Main thing that we're looking at is like a rational function here. Is there anything x is not allowed to be? So I would tell you one of the things we're looking for is like holes in the graph, jumps, asymptotes, things like that. Okay, this particular problem definitely has a couple of asymptotes in it because there's a couple places, and we'll get to this in a minute, but the bottom is not allowed to be 0, so x can't be 1. That's an asymptote. Right here, that one is actually okay with radicals because anything under the radical has to be greater or equal to 0. If this was like something with a minus, we would need to be careful of that. But that's the main things that we're looking at, okay, with domain is, are there any vertical asymptotes, holes, jumps, square roots of negative numbers? That's really the big thing we're looking for. So don't divide by 0. And next to that, I'll just put a little bit of information. A number divided by 0 is an asymptote. 0 divided by 0 is a hole in the graph. The other thing we can't do, don't divide by 0, and then don't square root negative numbers. And that's the main two things we're looking for, okay? And then you reduce it down if you need to. All right, so if you can like factor and cross out or whatever, you're going to reduce it down. Then we're going to find all our asymptotes and holes. Okay, so let's look at, right now we're just focusing on f. Guys, the bottom can never equal 0 because then, you know, it would be like asking where does x squared equal -1, and it can't, which means that with this particular function, there are no vertical asymptotes. And the domain is actually all real numbers. There also are no holes, okay? One other thing I want to talk about real quick is we called these before horizontal asymptotes. Or in here, this is talking about end behavior. Basically talking about what's happening at the edges of the graph. Is it like going up? Is it going to 0? Like what's it doing, okay? All right, if you guys remember, okay, let's see, where should I write this one? Over here. Vertical asymptotes, we let the bottom equal to 0 and solve it, because we know the bottom can't be 0, right? Holes are the places where top and bottom equals 0. And horizontal asymptote, now these are totally different. This is where we take the limit as x goes to infinity of our function. And I don't know if you guys remember this from before, but like, if the degree of the top is bigger, there's a slant asymptote. If the degree of the bottom is bigger, there's a horizontal asymptote of 0. And if they're the same, you use coefficients. Well, right here, because the top is bigger than the bottom, it does have a slant asymptote, and it's going to go down and then up. And the reason that I can tell that is, okay, if I take the limit as x goes to infinity of this, I get infinity over infinity, but the top grows faster than the bottom, and when I plug in two positives, it's a positive. So on the right, it's going to go to positive infinity. On the left, 2x to the third over x squared plus 1. Okay, it's a negative to the third divided by negative squared. A negative divided by positive goes to a negative infinity. It's going to go to a positive infinity on that side, negative on that side. Okay, so that's just going to kind of help us a little bit later. Okay. What's next? Let's see. X-intercepts comes where y equals 0. Now, with a problem like this where y equals 0, we're basically just looking where the top equals 0 when you have a fraction. So an x-intercept comes where the top equals 0, and a y-intercept comes from if we plug in a 0, okay? So if I set the top of this, different color, equal to 0, and I solve it, I get the point 0, 0. That's my x-intercept. If I plug in 0, 2 times 0 over 1 is 0, so my y-intercept is 0, 0. It just kind of gives us an additional point on the graph, right? So far, all I know about this graph is that it shoots off to infinity there, and there's a point at 0, 0, and there's no vertical asymptotes or anything like that. All right? Okay, now, everything else has to do with the first and the second derivative. And we got some room down here, so what I'm going to do is my first derivative, I'm going to do the first derivative test. Now, you guys, it gave me this because they didn't want to make you do the quotient rule on that. And so everyone told me to do the first derivative, and that's what it is. That's the first derivative, all nice and simplified. Okay, so, all right, we've talked about vertical asymptotes, holes, x, y intercepts, and behavior. Okay, and then this is all f prime number line. It tells me increasing, decreasing, and relative max and min. And then we're going to do an f double prime number line. So here's my f prime number line. All right, you guys? Now look, if you happen to have had any asymptotes, you would, or any undefined points, you would need to put them on the number line. Okay? But there aren't any. And then, okay. In order to find where the derivative equals 0, right? Again, with this, where derivative equals 0 is really just where the top equals 0. And if I go to solve that, I have, okay, if 2x squared is 0, or x squared plus 3 is 0, well, if I divide by 2, and I square root it, I get x is 0. This is one of my critical points. If I subtract 3, and I square root it, that doesn't give me anything. That's not possible. So my only critical point is 0. And now I'm going to plug in some test points. Now let's say I want to test -1, okay? -1 squared is positive. -1 squared is positive plus 3 is positive. -1 squared is positive, squared is positive. All those positive make it positive, okay? Now let's test 1. 1 squared is positive. 1 squared plus 3 is positive. 1 squared plus 1 is positive. So that's positive. That's like kind of weird, right? And 0, it's a critical point, but it's not an undefined point. So I'm going to go ahead and say that this is increasing negative infinity to infinity, like all the way through there. It's never decreasing, and there's no max or min, because it basically is just going like all the way up. So we don't really get an idea of what this graph looks like right now until we can do concavity. So right now, like, that's my best guess. I know it's not a line, but that's kind of what this is showing me. Okay, so now I'm going to take, okay, so now I'm going to take my second derivative. Okay, so the second derivative is -4x x squared minus 3 over x squared plus 1 to the third. Okay? And I'm going to make a sine line graph for the second derivative. Go ahead and label that. We know there's no undefined points. We know that when we set the derivative equal to 0, it's really just when the top equals 0. Okay, now this is where it's going to get a little bit fun, because when I solve this, I'm going to set -4x equal to 0 and solve that. And I'm going to set x squared minus 3 equal to 0 and solve that. So x is 0. So that's one of my possible inflection points. This one, x squared is 3. So x is plus or minus square root 3. So that's cool. That's a couple more possible inflection points. Okay? And now I'm going to test everything into there. Do you guys agree with me, before I start testing this, that no matter what, this is always going to be positive. Do we feel good about saying that? Not because of the cube, but because the x squared. X squared will always be positive, and plus 1 will always be positive, and then if I cube it, it'll always be positive. So I'm really only needing to test into those two. Okay, let's go for a really big negative number, like let's say negative 10. Negative 4 times negative 10 is positive. Negative 10 squared is 100, minus 3 is positive, so that's positive. Let's go with negative 1. Okay. Negative 1 times negative 4 is positive. Negative 1 squared is 1, minus 3 is negative. And then we'll go with 1. Okay, negative 4 times 1 is negative. 1 squared minus 3 is negative. And then I'll go with like 100. Negative 4 times 100 is negative. 100 squared minus 3 is positive, so it's negative. So you guys, my concavity is kind of like all over the place here. Concave up, down, which means all of those are inflection points, all right? So I'm concave up on the interval negative infinity to negative root 3 and 0 to root 3. I'm concave down on the interval negative root 3 to 0 and root 3 to infinity. And I have inflection points at negative root 3 something, 0 something, and root 3 something. And you guys know where we find those somethings? Whether it's inflection points or it's local max and mins, y values, we always go back to the original problem. Okay? Now, let me plug in 0 first because it's easy. 0, 0 is my inflection point. And I've already got that point on my graph because it was lots of x and y intercept. Now I need to plug in negative root 3 and positive root 3. 2x to the third over x squared plus 1. Okay, see if you can follow this along with me. I'll do positive root 3. I'm writing it like this because, well, you'll see. Okay, because I could take those, because if it's root 3 to the third, square root 3 times square root 3 is 3, 3 times 2 is 6, so it's 6 root 3 over, the square root of 3 squared is 9 plus 1 is 10. So it's 6 root 3 over 10, that is ugly. So I think I'm going to do that on, just get a decimal value with my calculator. So that's going to be, let's see here, 6 root 3 over 10. I'm going to get 1.039. And then you guys, with the negative 3, the only difference is it would make the top a negative. So that's going to be negative 1.039. Okay? So root 3, and root 3 is like 1.7. Root 3 right above 1, and then negative root 3 right below 1. Okay, so let's think about this. It's following this pattern where basically, you guys, I'm going like straight up, except the concavity is changing. So it's going concave up to there, and then concave down, and then concave up, and then concave down. So that's kind of weird, but I guess that's sort of what this is looking like. So let me put this in decimals and see how close we got. Okay, so here's what I got. I mean, I don't like love this picture. It doesn't show me the concavity very well, but it does. It's not a straight line. It has some concavity here, and then it changes, and then it changes, and it changes. Very, very like carefully. But anyway, so that's kind of how that goes. All right. Here's, I think, a little bit of a better example. Let's go ahead and look at example number 2. Roll through all the things. Okay. So, my domain, you know, we talked about this a little bit ago, where this is minus 1, if I were to factor that out. And so my domain is, it's all real numbers except x cannot be 1. The reason x can't be 1 is because there's a vertical asymptote there. So I'm going to go ahead and put a vertical asymptote when x is 1. Okay. Let's see. Okay, there are no holes on this one, because holes will come if you can cross something off on the top and bottom. There are none. Okay, x-intercepts are when the top is 0. The top is 0 at 2/3. So I have an x-intercept at the point 2/3 0, so I'll go ahead and put that there. Y-intercept is I plug in 0. So I get -2 over -1 times -1, which is -2 over 1, which is -2. So there's my y-intercept. Okay. End behavior has to do with like horizontal asymptotes. And if I go back to the original function, you guys, you can see the bottom is bigger than the top. So there is a horizontal asymptote at y equals 0 because the bottom degree is bigger than the top. So I'm going to go ahead and put an asymptote here. Where did the other asymptote disappear to? I'll try again. Here. And you might be like, what on earth? How are we passing through a horizontal asymptote? But we talked about this before. You actually are allowed to pass through a horizontal asymptote. You just can't pass through a vertical one. It's like there, but it's not there. Yeah, okay. Okay. Cool. That's nicely set up for us. Now I'm going to do my first derivative test. They were so kind as to give me this first derivative here. I'm going to go work right over here. Alright, so the first derivative is -3x plus 1 over x minus 1 to the third. Okay? Guys, when I go to draw my sign line graph, the first thing you have to do is take out your domain along that sign line graph. And I know there's an asymptote there, so I'm going to make it look like that. Okay? Next thing is I find any critical points. Well, setting this equal to 0, I mean, the bottom is already 0 at that asymptote. If I set this derivative equal to 0, my critical point is at -1 over -3, which is just 1/3. Okay? And now I'm going to do some test points on my graph. Alright, if I plug in 0, I get a positive over a negative. If I plug in, I guess 2/3, that's bigger than 1/3. If I plug in 2/3, it's -2 plus 1, that's negative, and 2/3 minus 1 is a negative 2/3. So that's positive. And then if I plug in like 5 or something, that's going to be a negative over a positive. Okay? So if I'm writing up my stuff here, I'm increasing 1/3 to 1. I'm decreasing negative infinity to negative 1/3 and 1 to infinity. And you guys look, I'm going down. There we go. I'm going decreasing, increasing, and then I stop, and then I'm decreasing. Okay? So 1 is an asymptote, so those aren't connected there. So I have a relative min at the point 1/3 something. And how do I always get that y coordinate? I go back into f. Okay? Geez, that's going to be a pain. Let me just do it over here. 3 times a third minus 2 over 1/3 minus 1 squared. So that's -1 over negative 2/3 squared. It's -1 over 4/9. And so that's like -9/4 squared. Okay, so there's a min at the point 1/3 -9/4. So it's like right there. Okay. So do you guys kind of feel like this is what I'm thinking for right now? It comes like down through here, takes that min, goes up like that. Okay, because we've also looked at the 10 behaviors. Whoops, I didn't go through my min. Down here, it's my min, and then it goes like that. Okay? Now let's see if this graph has any inflection points. So now I get to my second derivative, which actually simplified out a little bit. 6x over x minus 1 to the 4. Okay. Sine line graph for my second derivative. At x equals 1, I have an asymptote because that's where the bottom equals 0. If I do where the top equals 0, that's at 0. And then if I test, Can you guys agree with me that anything to the fourth will always be positive, just like anything squared will always be positive? So I'm going to have to test the 6x. So if I plug in -1, that's negative. If I plug in a half, that's positive. And if I plug in like 2, that's positive. Okay, so this is concavity. This goes concave down, up, up. So I'm concave up, 0 to 1, 1 to infinity. I am concave down, negative infinity to 0. And I have an inflection point at 0 something. Again, not at 1, that's my asymptote. And my inflection point is at 0, and then if I plug it back into the original, when I plugged in 0, I got -2, 0, -2. So that's my inflection point. So it's actually the same thing as this y coordinate. But can you guys see I kind of, I don't know, I drew that all right. Let's see. I came down, decreasing, increasing, but that was all concave up, and then once it's there, it switches to concave down. All right. And the other thing is on the other side. So look what's happening to the right of the asymptote. If I look here, the right of the asymptote, it is decreasing, and concave up. So if I think to myself, okay, what does decreasing concave up look like? Decreasing like that, maybe? So is there a good spot where that fits? Probably right like that. Okay? 3x minus 2. So let's take a look at this and see if we got this right. 3x minus 2. And once I factored out the bottom, it was just x minus 1 squared. Hey, would you look at that? I got an asymptote. I got that. This goes down. It hits a min right there. It hits an inflection point right there. Everything's all good. Okay? Sweet. Let's do one last one here. All right. We talked about with domain. So the bottom can never equal 0. But if you look, that will never equal 0 because I'm squaring it and adding 2. And I can't take it to the square root of a negative, but again, that wouldn't do it anyway. So my domain here is all real numbers. No vertical asymptote, no holes. X-intercept is where I set the top equal to 0, so I guess it has one at 0, 0. Y-intercept is where I set, no, I plugged 0 in. And 0 divided by 2 is 0. So that's also 0, 0. And end behavior. Now, this is interesting, you guys, because if I do limits to infinity to try my asymptotes, now we did stuff like this before. Try to remember back. And you remember when we're doing limits, we kind of only cared about the biggest terms. And we went like, oh, well, the square root of x squared is x. And since these are the same on top and bottom, 1 over 1 equals 1. And so I had this horizontal asymptote at 1. Dang it, sorry, I lost my spot. There we go. As I was approaching infinity. Okay. But if you guys remember these, it's like there's also, let's see here, the limit, as x goes to negative infinity of x over the square root of x squared, which is still 1, except when I plug in a negative infinity, I get a negative over a positive. So that's actually -1, which means that actually there's an asymptote on that side too. And so it's going to go toward 2 different asymptotes, which is kind of cool. So it has asymptote at +1 and -1, but basically the end behavior says the limit as x goes to infinity of f of x is 1, and the limit as x goes to infinity of f of x, negative infinity, is -1. Okay? Then I need to do my first derivative test, but I've got my first derivative right here. Alright, so it's 2 over the square root of x plus 2 squared 2 plus third. Perfect. You guys, there's no undefined points. If I were to set this equal to 0 on the top, there's no critical points. There's no points at all. What that tells me is this entire sine line graph is either always positive or always negative, so plug in anything. So I plug in 0. Well, 0 squared plus 2 is positive. The square root is positive, so the third is positive. The entire thing is positive, so I'm going to say this is increasing negative infinity to infinity, and there's nothing else. So all I know is this function is always increasing. Okay, now I don't know if it goes like that maybe, or if it has to stay inside the horizontal asymptotes and it goes like that maybe. So we'll see. Okay, now we do our second derivative. So I'm going to take this. Alright, negative 6x over the square root of x squared plus 2 to the fifth. And my sine line graph for my second derivative. Now, the second derivative equals 0 at 0, so at least it does have a change in concavity. If I plug in something less than 0, like negative 1, negative will be positive. Negative 1 squared plus 2 will be positive, so it's plus. If I plug in something like positive 1, negative 6 times positive 1 is negative, and positive 1 squared plus 2 is positive, so it's negative. So this goes concave up, concave down. So I'm concave up, negative infinity to 0. I'm concave down, 0 to infinity. I have an inflection point at 0 something. And when I go back in and I plug a 0 into the original, that's at 0, 0 is my inflection point. Okay? So guys, how do I draw something that is always increasing but changes from concave up to concave down? It has those asymptotes right there. Okay? So let's just check this one out, make sure we got it right. So we're going to go with x over... the square root of x squared, what was it? Square root of x squared plus 2. Square root of x squared plus 2. Hey, check it out, okay? Constantly increasing concave up to there, concave down after that, and it approaches 1 on this side, and it approaches negative 1 on this side. Okay? So there you go. Hopefully that lesson made sense for you guys. Just under 30 minutes. Let's go.